Now we're going to start our last set of notes. So this set of notes is about Markov chains. This set of notes starts with some technical definitions. So I'm going to talk through those definitions with you real quick, but I don't want you to worry too much about fully understanding these definitions at the moment. I think that if you'll just bear with me until we've seen some examples, then you can come back to this first page and hopefully parse it in a better way. So let's talk through some of the definitions that we'll need. So the first definition is that of a stochastic process. So a stochastic process is just some mathematical model that evolves over time in some probabilistic way. So you should think of the word stochastic here as just being synonymous with random. So this is a random process. An example of a stochastic process might be something like this. Let's say that we're driving around town, and every time we come to a stoplight, I flip a coin, and if it's heads, we take a left, and if it's tails, then we take a right. So that's a stochastic process. I can model that in a probabilistic way, but I don't know exactly where I'm going to end up over time. So this is just a purely probabilistic trajectory. We can talk about what the probability is that I land at certain locations, but ultimately this model has to involve some probabilistic transitions between our different driving states. A Markov chain is a specific kind of random process. So a Markov chain is a stochastic process in which the outcome of our next turn or the outcome of the next experiment that we do depends only on the outcome of the previous experiment or the current experiment. And this is sometimes called memorylessness. So what I mean by this is, let's say that we have three states like A, B, and C that we can be in. And let's say that we're going to be in one of these states each day. So one day we might be in state A, the next day we might be in state B, and so on. So a Markov chain would go through these states in a probabilistic way. So if you're in state A, you would have some probability of staying there, some probability of bouncing to B, and some probability of bouncing to C. So we're going to probabilistically bounce back and forth between these states in the same way that we were probabilistically bouncing back and forth between taking lefts and taking rights in the example that I gave you a second ago. But in a Markov chain, the next step that you take depends only on the state that you're currently at. So if I wanted to know the probability that I'm about to step to B or the probability that I'm about to step to C, that only depends on the current state that I'm standing at. It doesn't depend on what we did yesterday or last week or anything like that. And that's why these are called memoryless processes. So we're going to focus on models for these memoryless processes. And there are two equivalent ways of describing these models. So one is with a nice diagram, like this one up top, and one is with a transition matrix. So these two bits of information are equivalent to each other. We'll be able to translate from the diagram to the matrix and vice versa, in the same way that we might have been translating from a system of equations to a matrix and vice versa. So these two bits of information are exactly the same. Let me try to explain what both of these things are saying. So remember that in a Markov chain or in a Markov process, the next step that you take only depends on where you're currently standing. So let's pretend that the current state is A. So for that, we're going to look at the node that says A. And you'll notice that there are several arrows that are either going toward A or away from A. So the arrows that are coming out of A are telling us what the probability is of making that arrow as our next step. So if we look at maybe this arrow, that's an arrow that says 0.5 and it's pointing from A to B. So what that means is that if you're at A today, then there's a 50% chance that you will be at B tomorrow. So this is telling you the probability that you'll make that transition on your next step. And similarly, there is a 20% chance that you will move from A to C tomorrow. And notice that there are also self arrows. So there are arrows that just go from A to itself. What this means is that in this case, there's a 30% chance that you would go from A today to still being at A tomorrow. So we can think of each of these arrows as sort of recording what's happening on a given time step. And a transition matrix is encoding that same information. A transition matrix will always be a square matrix, and the sum of the entries in any row will be 1, because that's representing the probability of transitioning from this row state to each of these column states. So notice that in the example I gave up here, we have that there's a 50% chance that if you were at A right now, you would transition to B tomorrow. So that's a 50% chance of going from a state A to a state B. And that same percentage also exists in this matrix down here at the bottom. It's this entry. So the entries in this transition matrix are telling you the probability of transitioning from this state to this state. So I could read this as saying the probability of going from A to B is 50%, the probability of going from A to C would be 20%, and so on. So each row is telling you the current state, and the columns are telling you what the next state will be. So let's look at some examples, because I think that will help a lot. So here, in part 1, it just says, is this matrix a valid transition matrix? And does it match the given transition diagram? So to check whether it's a valid transition matrix, we just need to check the properties that we had on the previous page. So I need to check whether this is a square matrix and the sum of the entries in any row is 1. So we'll check those two things. Clearly this is a square matrix, it's a 3 by 3 matrix. And now we just check that each row sums up to 1, but it does. So if you notice that if you add these up, you would get 0.6 plus 0.1 plus 0.3, that is 1. And similarly, the sum of these other two rows is also 1. So each row has a total of 1, and that's good because each row is supposed to represent the transition probabilities away from the given state. So maybe this would be the transition probabilities away from A, for example. And that top row is telling us that there's a 60% chance that if you were at A today, then you'll be at A tomorrow. And then there's a 10% chance you'll be at B tomorrow, and a 30% chance you'll be at C tomorrow. So this is a valid transition diagram. And then the second thing is, does it match the given transition diagram? Or sorry, I should say this is a valid matrix. And now we want to know whether this matches the diagram down below. And to check that, all that we need to do is we need to check whether each of these rows, so I labeled the rows incorrectly, I was just making up state names, but in the diagram they're given to us, we know that the 3 states are called X, Y, and Z. And when we get to the word problems, I'll tell you what some possibilities are for these different states. But for now, we're just going to label them with single letters. So let's check this first row to make sure that it's compatible with this diagram. So the first row of the matrix is telling you that the probability of transitioning from X to X is 60%. That's also what this arrow is saying. So that's valid. And then the probability of transitioning from X to Y from the matrix should be 10%. That's also what we get from the corresponding arrow here. And then the probability of transitioning from X to Z would be 30%, and that's what we get from from this arrow here. This arrow is telling us that there's a 30% chance of transitioning from X to Z. So at least for the X terms, this does match the diagram. And you can go through, I would recommend maybe that you pause the video and check these 6 entries to make sure that you can identify what each of these entries corresponds to in the diagram. So for example, if I was to look at this one, that's supposed to be the probability of transitioning from a Z to a Z. And I can check in the diagram for that. I would look at Z, and then I would look at its self arrow, which is the arrow that goes from Z to Z. And I notice that its weight is 0.8. So if you'll check, this does actually match up completely with the transition matrix. So these do match. So I'll say this does match the transition matrix. Okay, so next let's take a diagram and translate it into a matrix. So here it says, is the diagram a valid transition diagram? If so, what's the corresponding transition matrix? Now here, there is such thing as validity for a transition diagram. So here, remember that the arrows that come out of X, for example, are supposed to be describing the probability of going from X to X or going from X to Y. So if we look at the arrows that are coming out of a particular node, those arrows, their weights have to add up to 1. So if we look at our transition away from X, then notice that here we have a 60% chance of going from X to X and a 40% chance of going from X to Y. And those do add up to 1. So that describes a valid probability distribution on what we're going to do next after leaving X. And similarly, if we look at the arrows that are coming out of Y, then we have a 70% chance of going from a state Y to a state Y on our next step. And we have a 30% chance, if we were currently at state Y, of transitioning to X for our next step. So because 70% plus 30% is 100%, then that also gives us a valid probability distribution of what we're going to do next after being at state Y. So this is a valid transition diagram. And that's just because all of the arrows that come out of a particular node add up to 1. Just like each of the rows that we were talking about in the transition matrix have to add up to 1. Because both of those things are describing the probabilities of leaving that state as your current state and moving into those other states. So this is a valid diagram, and now we want to make the corresponding transition matrix. Now you can put these states in whatever order that you'd like to. So normally if they're just given single letter names, we would label them with just an alphabetical order. So I'll call X our first state and Y as our second state. And here we'll have a 2 by 2 matrix. I'll label the rows and columns, but you don't necessarily need to label the rows and columns. It's probably going to be clear from context what your rows and columns represent. But here, remember that your first row is telling you the transition probabilities away from this state. So if I wanted this top left entry, maybe think about this yourself and commit to what you think this answer should be. But what I would get for this entry is a 0.6. And that's coming from this arrow, which tells us that if X is our current state, then the probability that X is also our next state is 60%. And similarly, we know that we have a 40% chance of going from X to Y, so that should go in the X row and the Y column. Because remember, this is the probability of transitioning from this state to this state. So I would look at the arrow that goes from X to Y for that information. Similarly, if I look at the Y row, here, this entry, be a little bit careful. This is the transition from Y to X. So we would look at the arrow that corresponds to transitioning from Y to X. That has a 30% weight. So this would be a 0.3. And we also know, even if we didn't want to look at the diagram, we also know that the rows in a valid transition matrix have to add up to 1. So even if I didn't have this part of the diagram, I could still answer this question. I could still well, at least this part of the question. I could still fill in that last entry because I know that this bottom row has to add up to 1. And therefore, there has to be a 70% chance that we go from Y to Y. So this is my transition matrix. And lastly, we can do the same sort of translation in the other direction. So actually, this is the same one. So you can make a transition diagram from a matrix, and we'll see some examples involving that in a bit. But these are essentially just two different ways of relaying the same information. So here, if I wanted the T13 entry of the transition matrix, I can choose specific entries if I want by just remembering what each of the rows and columns represents. So I'm just going to label my rows and columns again. But here, if I want the T13 entry, that would be in the first row and the third column, so this would be T13. And therefore, T13 should represent the probability of transitioning from the first state to the third state. So this is from the first state to the third state, or in other words, from X to Z. So if you want, you can pause the video and commit to an answer now, just to make sure that you're understanding what's happening so far. And notice that here, the prompt did tell us exactly what the ordering was. It's important that if you order the rows in a particular way, that the columns have the same order. So if you ordered your rows as X, Y, Z, you would also need to order your columns as X, Y, Z. So here, we are transitioning from the first state to the third state. So in other words, from X to Z. And we would look for the corresponding arrow here. That's the arrow that transitions from X to Z, and it has a weight of 0.2. So the probability of transitioning from an X to a Z, if you're currently in state X, is 0.2. So that's the basics about translating from transition diagrams to matrices and vice versa. Next, we'll look at some word problems involving building transition diagrams and matrices. And there, I think you'll see some of the situations